Okay, in this video I wanted to spend a little bit of time to talk about the index notation that I introduced in topic 1. And I also wanted to maybe lay some breadcrumbs for what we're about to do in the next lesson, which is actually to code the heat equation. So there are some non-trivial things you really need to do to set yourself up for success, both in in actual equations, but also just in the mindset. So what we're really talking about doing is going from a continuous domain and let me, sort of emphasize what I mean by that. So in this continuous domain, let's say that we have some derivative ux of xt, and that of course is equal to the partial derivative of u, which is a function of x and t with respect to x. And in this particular derivative, we're talking about, let's say x is between 0 and L, and t is some value greater than 0. So obviously, understand too that, if we're actually talking about an initial boundary value problem, we have initial conditions and boundary conditions, and so we wouldn't include the endpoints. So, if we're talking about this rod in one-dimensional space, which is what the one-dimensional heat equation is, we have x equals 0, which is one end of the rod, and x equals L. And we have every value, we have access to every single value in between x equals 0 and x equals L in this continuous fashion. So when we're coding in numerical methods, and actually just one more thing about the continuous domain, when you get a solution to the initial boundary value problem, you are getting a function of x and t, and again, you have access to all of those values of x and t. So moving on to this discrete domain, and this is where computers live. So computers must live in this discrete domain. We don't have time to choose every single value in between 0 and L. You would be here forever, literally. So what we need to do is we need to break up all of the domains that we have access to, the space domain and the time domain, into some discrete values. So let's start talking about the spatial domain. And so let's say, again, we have this one-dimensional rod. And it's fine if we start at x naught equals 0. But then I have an x1, and I have an x2, and I have an x3, and so on until I'll do an x4 just for fun, and so on until I get to the n, which is x sub n, and that is equal to L. But I do not have an x 1.2 or 1.5. I have no information in between x1 and x2, and now you can kind of see why it's important how large or how small delta x is. So what we're going to do is swap notation just a little bit and use this index notation. And for the spatial domain, I'm going to use the index I. So I can write, I've actually already done this, but you can see x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. So I starts at 0 and goes all the way to n. And so how I can write this spatial domain, and just to emphasize, is x sub 0 is equal to 0. And actually, let me write this the other way around. 0 is equal to x sub 0, which is less than x1, which is less than x2, which is less than x3, which is less than x4, ... which is less than x sub n. So this is a discrete domain. That's how this works. And so delta x is equal to, in this index notation, remember, so for example, x sub 2 minus x sub 1 would give me delta x. X sub 3 minus x sub 2 would give me delta x. So let's just pretend that I'm hanging out on x2, right? So it would just be x I plus 1 minus x of I. So that's really all there is to it. I think it's intuitive. And then we can do the same thing with the time domain, or temporal domain if you want. And I'm going to use the index j. And in the same vein, 0 equals t naught, which is less than t1, which is less than t2, which is less than t3, dot, 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 which is less than t sub n. And this is going to equal some big T. And this really is the simulation stop time. So if you were told to start the simulation, 0 and, go all the way to t equals 10, big T would equal 10 at that point. And you absolutely need a stop time, or again, you will be here forever and your computer will blow up. So similarly, delta T is equal to T j plus 1 minus j, minus T sub j. So the choice of index doesn't really matter. You could use P and Q for all I care. It doesn't actually matter. A lot of times in numerical methods, when you get into the more complicated ones, for time they use n, and for the spatial directions they use I, j, and k. I don't really care which one you use. It doesn't matter to me, just as long as you're consistent and you define what you define your indices. Okay, so then how do we relate that to this derivative in the continuous domain? Well, in the previous reading, what you saw is, we're going to need this for a second. So using indices, one thing that we're going to need access to is what is x plus delta x. So if you just follow the formula that we've created up here, x is the current x, so that would be x sub I. And I'm going to add to that x delta x, which is x sub I plus 1 minus x sub I. And this is equal to x sub I plus 1. I think that it's also intuitive if you look at x plus delta x, right? You're at x2, and you move delta x to the right, you get to x3, which was, it's just I plus 1. So I think, again, this is quite intuitive, and I cannot understate just how important and how useful and how helpful using these indices will be to coding loops. So one of the reasons why I introduced summation notation earlier this semester. Just really, I hope that this makes sense to you because it will be really helpful to you in coding. All right, so if I were to write the derivative ux is partial derivative of x, or of u with respect to x, and I want to figure out what ux is at the current I, or the current x and the current time. So x sub I, t sub I. Well, that would be equal to, so this is what we talked about in, and actually here, I apologize. Let me actually show you what we did earlier in the reading. ux, xt. I'll write it in the more familiar notation first, just so we can actually compare and contrast. It's approximately equal to u x plus delta x t minus u x t divided by delta x. Now, I'm leaving the delta x as is and not writing it as x sub I plus 1 minus x sub I because the delta x is usually given. It's almost always given, at least at this level. And so this delta x right here, this is actually going to be a number. This is a given in the problem, as is the simulation stop time, for that matter. And what I usually do is when I code, I use dt for delta x, dx for delta x, instead of using h or k or some letter. And the reason why I do that is sometimes, you then get tired and you're trying to figure out what this h represents, whereas delta x is very obvious what it means. So usually I'll use this as my MATLAB variable for delta x. I'll also use dt, little d, little t for delta time, or for delta t. So anyway, it's completely up to you. So now let's write this difference quotient, this forward difference derivative in x in this index notation. So this is completely equivalent, and I will write ux x sub I, t sub I, as I said earlier before I erased on you. X sub I, t sub I would be the current values of x and t. And that's going to be equal to, okay, so earlier we already talked about this. This is u, and x plus delta x in this index notation is just xi plus 1, comma, tj, because it's the current time, but we're just moving forward in space. And then subtract off u at the current x, current time, divided by delta x. Now we can actually make this simpler, because remember earlier where we had f of x sub I, you could write that as f sub I. We're gonna do the exact same thing. So now I'm just gonna write this as u I plus 1, comma, j. And this indicates u evaluated at the next x, so the right, the x value to the right of where you currently are in the current time, minus u, and this will be I, comma, j, divided by delta t, or delta x, sorry. And so I think this notation is very compact, and it's just much easier to work with. You don't have to, the more things you write down in numerical methods, the more likely you are to make a mistake. So this compact notation is actually really helpful. And I wanted to show you one more that you don't necessarily have to use. It's completely up to you. But when you get more complicated, and what I'm talking about is where your function is, your ux or u is a function of x, y, and z and t. It can get really confusing. The subscript can get very crowded very quickly. So what you can actually do is use superscripts to represent time. And I think that does kind of make things less crowded. So u, I plus 1 superscript j, minus u, I superscript j, divided by delta x. And you can see that if you did have another spatial direction, let's say you had, you had y, and you could let, I don't know, the index for y be k or something. In the subscript, you'd have an I and a k. In the superscript, you'd have j. So it does sort of declutter some of your notation. So I don't really care which one you decide to use. Either is fine. Either works. Just please make sure that you understand how your notation, your chosen notation, does actually work.